Welcome to another lecture. This is lecture 3 in our series here. I'm going to start by reviewing some of the things that we discussed last time. We had discussed the equations of motion that describe motion in 1 and 2 dimensions, and we looked at both the x and the y direction, and we discussed the fact that the velocity would need to be decomposed into your x component and your y component using your sine and cosine functions. We can describe the velocity of an object as a function of time or its position as a function of time, and we can also use time-independent equations to look at the relationship between the velocity, the acceleration, and the displacement. And then we took these equations and we applied them to the special case of free fall. And in free fall, we discussed the fact that the only acceleration present is going to be that due to gravity, which means there is no acceleration term present for the horizontal direction. There is only acceleration in the vertical direction, and that acceleration is equal to minus g, which is to say minus 9.8 meters per second squared. Okay, so based on all of that, let's do a couple concept checks here and make sure that we get the idea behind this special case of free fall. So again, whenever I present these kind of multiple choice questions to you, you can feel free to pause the video, think about what the answer is, make a guess at it, and then unpause it and see if it corresponds to the correct answer. So in this question, we're asking about the difference between dropping a ball and throwing a ball downward. Okay? After you release the ball, however, once you let go, the only acceleration the ball is going to feel is that due to gravity. So the correct answer here is B. You're not continuing to accelerate it. Yes, you may have accelerated it to an initial downward velocity as you pushed on it downward, but as soon as you let go, it is under the influence of gravity only. It's no longer under your influence, and so the only acceleration you have is that due to gravity, 9.8 meters per second squared. Of course, it would have had an initial velocity, which is not the same as when you drop it, but velocity and acceleration are different, right? Okay. And so a similar question might arise when we drop different kinds of objects. What if we were to drop a brick, for example, instead of a ball? Okay, again, you can pause this, and once you have thought about it, hopefully you can remember that the correct answer here is B, that the acceleration rate due to gravity is a constant near the surface of the Earth, which does not depend upon mass. So it won't matter if I drop the brick or the ball, they're still subject to this 9.8 meters per second squared. Of course, some objects that have a lot of air drag, such as a feather, are going to be influenced by something other than just gravity, right? They're going to be experiencing something that will serve to decrease the acceleration rate. But we're not considering cases like that quite yet. We're just considering cases in which the only acceleration present is that due to gravity. That's what we're defining free fall as. So for our purposes, we're ignoring any air drag. Okay? When we ignore air drag, that acceleration rate is the same, and it doesn't really matter what kind of object we are dropping. All right, so let's consider another case in which we throw a ball upward with an initial speed of 20 meters per second. What we want to know is what's happening at the top of its trajectory. So go ahead and pause it if you would like so that you can think about this. And when you've returned, hopefully you've been able to conclude that the correct answer is C here. Now, if not, don't feel bad because this does seem maybe at first glance to be counterintuitive. Most of us are able to deduce that at the top of the trajectory, the velocity is equal to 0. Okay? But a common misunderstanding is that that means the acceleration is equal to 0. Just because velocity is equal to 0 does not mean necessarily that acceleration is equal to 0. In fact, you can think about it this way. If the acceleration was equal to 0 at the top of the trajectory, what would possibly make it come back down? Nothing, right? It needs some acceleration in order to come back down. So saying the acceleration is 0 at the top of the trajectory would result in the object just hanging there in midair, which doesn't make sense from our experience. Another way to think about it is that the velocity vector is changing directions at the top of the trajectory. And remember that acceleration can slow an object down or speed it up or change its directions. So although it seems as though the velocity vector is disappearing, it's really in the process of changing directions, and that's what the acceleration vector is doing to the velocity at that instant in time. It might be clearer to see that if we mentally go through the process of thinking about the velocity and acceleration vectors as the object completes its motion. So let's say that we take that ball and we throw it up in the air at 20 meters per second. At that point, you've got a sizable velocity vector. 20 meters per second is pretty fast. And you've got this acceleration due to gravity. Anytime we're on the surface of the Earth, the gravity is always relentlessly pointing downward with this magnitude. Okay, we can't just turn gravity off, so we're always going to have this acceleration vector through every moment of the object's motion. What that does as the object is moving up is it's going to slowly decrease this velocity vector's magnitude. So if we look a second later, we see that the velocity vector is still pointing up as the object continues up, but now it's decreased in magnitude because the acceleration has been working to change the velocity and make it less in the upward direction. And as we continue on, it shrinks even further and further until we reach that point where the velocity equals 0 at the top of the trajectory. The acceleration is continuing to change the velocity though and change its direction so that now the velocity vector will start to point down, and the change of velocity will continue as that acceleration vector remains the same throughout this motion, while the velocity vector now increases as it falls downward. Okay, so hopefully that makes it a little clearer that there's nothing magical about that moment where the ball is at the top of the trajectory in terms of the acceleration. We've always got gravity pointing downwards. That is a rule of any kind of free fall motion. Okay, so let's take this example and now apply it to some problem that you might have to solve related to this ball that's being thrown up with an initial speed of 20 meters per second. So let's say we want to know at what instant in time this ball is at a position where it is 10 meters above the point from which it was thrown. In order to do this, we're going to follow the steps we discussed last time, which is to draw a picture and define a coordinate system, step 1 and 2. We'll go through all 5 steps in this problem-solving process. Again, you don't have to draw anything too fancy, but sometimes it helps to sketch the situation, and then define a coordinate system. The convention is typically to have positive y pointing up, and we may as well start the ball at the origin, y equal to 0. Okay, that's where it's at time equal to 0. At a later time, it's going to be at this position where it is 10 meters above its starting position. And we want to know what is that time. Okay, so the next step in our process, our problem-solving strategy, is to think about what it is that we know and what it is that we don't know. So of these possibilities that are written here, what do we know and what don't we know? Well, we know the initial position. In fact, we set it to be equal to y equal to 0, and we know then that the final position, if it's 10 meters above that, is equal to 10 meters. We've also been told that the initial velocity is 20 meters per second. We do not know what the final velocity is when it's at this point, which is 10 meters above its starting point. We do, however, know what the acceleration rate is because this is a free fall problem, and all acceleration rates in these free fall problems are 9.8 meters per second squared, little g. but we also don't know the time. And in fact, the time is our target variable. This is what we were asked for. This is what we're trying to solve for. Okay, so the next step in our process, step 4, is to identify which concepts might apply to this kind of motion. We do not have constant velocity because there is acceleration due to gravity, right? And we do not have really two-dimensional motion to worry about. We are just throwing the ball up and down, so it's throwing it up and it's coming back down. So this is really just one-dimensional motion, and it is free fall motion as well. Okay, so once we've identified these concepts and our knowns and unknowns, we can go about choosing which equations we should use based on this. So there's a couple possibilities. We have many equations of motion related to the special case of free fall. Again, you can pause the video if you want and think about which of these equations you might want to use. When you come back, we can hopefully immediately eliminate choice D. Why? Well, nothing's happening in the x direction. We don't need to worry about the x direction at all. There really isn't any motion in the x direction. That leaves us with 3 other possibilities. Choice C may seem the most obvious at first because here's my t right here. But the problem is I also don't know the final velocity, right? So I could do one of two things. I could use A first, and that would be to find the final velocity, and then I could plug that final velocity into this equation C, and then I could solve for the time. So that would be a two-step way to do this. Another possibility would be to solve it in one step, which is what I'm going to show you, in which case I'm going to use this equation that describes the y position as a function of time, because in this equation I don't need to know the final velocity. I do need to know the initial and final y position. That's no problem. I know that. I know the initial y velocity, and I know little g. So the only thing left to solve for here is time. That allows me to solve directly for the time in one step. And so that's how I'm going to solve this particular problem. So the next part of this is to implement that equation and chug through the math. Now, this equation is a quadratic equation. Sometimes when we use this equation, depending on what we know and what we don't know, or if there's initial velocity or not, we may need to use the quadratic formula. For those of you who don't remember, the quadratic formula is this, based on this template of the equation. Now remember that in this version of the equation where we use the quadratic formula, all the terms are on one side of the equation and you have 0 on the right hand side. So in order to get this equation to follow the same format so that we get our signs correct, we need to put everything on one side of the equation so that we have something like 0 equal to minus 1/2 gt squared plus v naught y t minus y naught. Okay? And then in this version of the above equation, now we see that our A is minus 1/2 g. Our B is v naught, and our C is minus y naught. Okay, you could even rewrite that if you would like to, because it's a little bit awkward. You could write this as plus y naught minus y. Okay, whichever you prefer, as long as you keep that sign straight. And when you carefully obey those signs and put them into this quadratic formula, by the way, a sure sign that you've messed up a sign is if you have some negative underneath the square root. Although that's not even always the case, because it's possible that, you may be looking at a situation in which it's not possible. And so you would have you would have an imaginary root here. But most of the time we'll make sure that our equations work out for you so that you have a positive underneath the square root here. And if there's somehow a negative, don't just brush it under the rug. Don't just brush it under the rug and turn it into a positive. Look and see where you may have messed up a minus sign. Okay, so when you do this, for this particular example, you will find that there are two solutions, as is always the case with these quadratic equations. We've got a plus and a minus sign here. So these two solutions, sometimes we can throw out one as not being sensible. For example, if we had a time that was less than 0, we can say, well, that doesn't make physical sense, so that's not a solution I will accept. But in this particular example, both of the times are positive, so there's no reason to necessarily reject them. So we've got to think about why there could be two solutions in this case. For this particular example, we're looking at what time the ball is at a certain location. Well, the ball goes up and then it comes back down. So it would make sense that it passes a particular point twice, once on its way up and once on its way down. Okay, so then the last step is just to ask ourselves if these times make sense. If you are throwing the ball up at a rather rapid speed, that it could reach 10 meters in about 0.6 seconds and come back down in 3.5 seconds. Perhaps there's a little bit of judgment here, but it doesn't seem outlandish. We can say that it meets the sensibility test. Okay, so that is an example of how to solve a problem in one dimension with free fall, but really a form of free fall is something else that we call projectile motion. It's really the same in the sense that the only acceleration present is that due to gravity, and the only thing that makes it different is that we are adding in some horizontal motion so that it's a two-dimensional motion. But remember that in the horizontal direction there is no acceleration, it's just a constant velocity motion. So the constant velocity in the x direction plus the free fall due to gravity in the y direction work together to create a trajectory that is characterized by a parabola, as you're seeing here with this snowboarder. Okay, so let's think about that motion in terms of some graphs of position versus time, velocity versus time, and so on. So if this is our parabolic trajectory of some object which is in projectile motion, this is a position versus time graph. So what's happening then with the acceleration versus time? Okay, I'll give you a minute if you want to pause it. And when you come back, hopefully we can conclude that the acceleration is going to be just a constant 9.8 throughout time. Okay, that corresponds to choice A. Now let's ask ourselves about the velocity. What is happening with the velocity as a function of time? Well, whatever was happening had to do with some positive amount of velocity to begin with as the object is heading up and over, and then negative velocity as it's heading mostly back down. And so that corresponds to choice D. All right, now that we have some graphical understanding of what's happening, let's do an example in which we apply the equations of motion to two-dimensional projectile motion. So let's consider someone who is going to do a cliff jump off a 15-meter cliff. They get a running start, have an initial velocity that is at an angle of 30 degrees from the horizontal. And what we want to know is how far away from the bottom of the cliff are they horizontally when they hit the water. Okay, you don't want to be too close. So step one is to draw a picture. Again, doesn't have to be fancy like this photo, just a rough sketch is fine. And then you want to define a coordinate system to go with that. Okay, so we're going to place the initial velocity vector here at the edge of the cliff, and we want to make that a 30-degree angle from the horizontal, right? And the cliff itself is 15 meters. So we've sketched out the situation. In order to use the equations of motion, I'm probably going to need to resolve this velocity vector into its components. I'm going to want to know how much is the initial v in the x direction and how much is it in the y direction. Okay, in order to do that, we use our sine and cosine functions. Okay, so we have some amounts here. We see that it's mostly horizontal and a little bit vertical. And then we want to figure out how far away the person is from the bottom in terms of their horizontal distance from here to here. However, we don't really know the time to plug in here, right? We don't know what the time is, so that even though we have this v naught x, we cannot solve for delta x directly. We've got to do something else first. So what we can do, and this is often the trick to projectile motion problems, I'm just going to lay that out there for you. This is almost always what you're going to need to do, is to look in x direction to find something and then plug it into the y direction or vice versa. Oftentimes it involves solving for the time and then plugging the time into something else. So we have another equation we can use, which is this one, which describes how the vertical position changes as a function of time. And if I use this equation, I can now solve for time in a similar way to what I did in the previous example. So I'll let you chug through the numbers and verify this on your own, but you should find, when you solve for the time in this equation, that you get two possibilities, just as we did in the previous example. One is negative 1.51 seconds, and the other is positive 2.02 seconds. Okay, we can reject the negative one. That doesn't make sense to have a negative time, so we accept this positive time of 2.02 seconds. Given that it takes roughly 2 seconds for the person to fall from this top 15 meters down to the bottom, then that allows us to plug the time into this equation. Okay, when I do that, I find that I come up with a distance, a delta x of 8.08 meters. And so the last step in my problem solving process, step 5, is to ask if this is sensible. Okay, 8.08 meters is about 26 feet. That seems like a reasonable distance, and so we will accept that as passing the sensibility test, and we've been able to solve this problem by using equations both in the x direction and the y direction. Okay, so the last question I'll leave you with in today's lecture is to think about what would happen if the person had jumped straight down versus someone who jumped as this person did with some initial horizontal velocity. If they were going straightly horizontal or straight down, what would be the difference in who would hit the bottom first? Okay, think about that, and we will discuss it next time.